Okay, hey guys, welcome to lesson 2 for chapter 7 and 8, um, our bonding unit. Today we're going to talk about, we're going to talk about covalent molecules, and we're going to draw them using Lewis dot structures, a lot like we did with individual atoms, but this time we're going to we're going to show covalent bonds and multiple atoms in a single compound, and we'll do some ions and some other stuff. It'll be good. You guys will enjoy this. Okay, so let's get this set up. There we go. So yeah, here's chapter 8. Cute little drawing there. Two hydrogen atoms sharing a pair of electrons between them. If this were to be drawn as a hydrogen molecule, kind of not like this, it would just be hydrogen bonded to a hydrogen. And we'll get to that and figure out how we're going to draw those things today. So here we go. So our objectives really are to describe bonding in molecular compounds, covalent bonded molecules. We're going to define single, double, and triple bonds. And we're going to draw Lewis dot structures or Lewis dot diagrams for several covalent compounds and learn how to do that. So molecular compounds are compounds that are held together by sharing pairs of electrons. So they have covalent bonds between them. So they're going to do this by trying to attain noble gas configurations. For hydrogen, that's going to be attaining the noble gas configuration. For helium, for other atoms, it's going to be neon, argon, krypton, and so forth. With covalent molecules, molecular compounds, molecules, they're actually going to share electrons to attain that noble gas rather than gain or lose them like they would if they were ionic compounds. So looking down here on the bottom, there are individual, in this one little diagram, there are individual hydrogen atoms out here. Got lots of little arrows going on here. Individual hydrogen atoms. And so the carbon atom only has 4 valence electrons around it right here. 1, 2, 3, 4. To attain a noble gas configuration of neon, it's going to need 10. And so what it does is it shares a pair with hydrogen, a pair with hydrogen, a pair with hydrogen, a pair with hydrogen. And it would be drawn like this structure over here on the right. I'll go over this again, but each one of those lines or dashes between two elements represents a single shared pair of electrons. And that's kind of, I'm going to show you the rules and stuff about how to draw these in that fashion. So covalent bonds are those shared pairs of electrons. Like I said, a dash is used instead of a pair. You could certainly use or you use more than one dash depending on how many pairs of electrons were shared between two atoms. If you see electrons between the atoms, those are called shared pairs. If you see electrons outside the shared pair of electrons, those are called unshared pairs, obviously, or what I'll term them most of the time as are lone pairs. And so we'll call them the lone pairs. If you look at the chlorine atom down here, on each one of the chlorines, there are 3 lone pairs. So there are 6 electrons not involved in bonding. And those will play more of a role later on in the unit when we discuss polarity and the behavior of attractions between molecules. But for right now, we'll just call them lone pairs or unshared pairs. So here are 3 different diatomic species, 2 of them diatomic, and then of course HCl. So you see that they have individual bonds between them, single covalent bonds between them. That is a sharing of a single pair of electrons. Usually one donated from one atom and one donated from another atom. That's not always the case, but it is in the case with all of these. And so those are all single covalent bonds. So atoms must have to share electrons from other species in order for them to become, or for them to be more stable. And usually that is to attain noble gas configuration of 8 or 2 electrons in the case of hydrogen. If there are more than one shared pair, it could be a double or a triple bond. If 2 pairs of the electrons are shared, we call it a double bond. Yeah, it makes sense. 2 pairs of electrons shared, it's a double bond. If 3 pairs of electrons are shared, it is a triple bond. And there's a couple of examples of them down below. Oxygen has a double bond between it. Carbon dioxide has 2 double bonds, and the nitrogen, of course, with a triple bond between each of the nitrogens. If we look at, let's just look at the oxygen molecule right here. I'm going to draw it over here to the side. And it doesn't really matter if you put the electrons on edges like this, or if they're at little angles. It looks like on the bottom of the circled one down here, that they're like at 120-degree bond angles between them. We're not really concerned that you guys do that necessarily, but they do have to have the right numbers of electrons. So if I look at the number of electrons that are around this oxygen and remembering to count the dash as a shared pair of electrons, I end up with 2, 4, 6, 8 electrons around that oxygen. And the other oxygen also has 8 electrons around it, attaining a noble gas configuration congruent with neon. And so that makes sense. Nitrogen, same thing. If you look down here at the nitrogen, I've got 2, 4, 6 in the bond, and then 2 in an unshared pair or lone pair. And then I also have 2, 4, 6 in the bond and an unshared pair on the other side as well. So they have to attain noble gas configuration, and it doesn't necessarily have to be single bonds. They could be single, double, or triple bonds. There won't be any with 4 bonds, but single, double, or triple. So there are some rules for writing electron configuration, or electron configuration, for writing Lewis dot structures. Now, we did that already with the individual atoms, but when you're doing multiple atoms, it's a little bit different. You're going to want to use something that you can erase, because you're going to make mistakes. Even when you're not making mistakes, the procedure for figuring out what you need to draw will require erasing. So make sure you have a pencil when you're doing this. What we're going to do is have a series of steps, and you can't really skip any of these steps. You need to follow them closely, and hopefully you do them in order. That would be very helpful. You'll get through them more quickly with fewer mistakes, but make sure you don't skip any steps. So the first thing you do is add up all the valence electrons from the atoms that are involved in the molecule. It doesn't matter where they come from. You don't have to keep track of how many came from carbon or hydrogen or whatever. You just add them all up, get a total. If you're working with an ion, don't forget, if it's positive, you're going to have to take electrons away. If it's negative, you're going to have to give it additional electrons. You're going to use a pair of electrons to form bonds between them with a dash. We'll do this. And then anything on the outside of the dash will have a lone pair, and you'll put those together as pairs. There are times when we don't do that, but for right now, everything's paired up. Arrange the remaining electrons to satisfy the duet rule for hydrogen, meaning it gets 2 electrons to be isoelectronic with helium, and everything else will get 8 around it until we have breaches of the octet rule, but that will be in the next lesson, not today. You cannot create or destroy electrons. You can merely create double or triple bonds, and I'll show you how to do that. If necessary, like it says, change the bonds to double or triple. And we'll see if I can remember. Those of you that are Aiken kids, she always has little cute ways to do stuff, and I just don't have those things, but I'm going to try to steal some from her. Okay, so let's do an example. So the first thing on that list was to add up the number of electrons that are from each of the species, each of the atoms. Valence electrons is worked on, not total electrons, but total number of valence electrons. Hydrogen is in column 1. So from one hydrogen, we have 1 electron. From the other hydrogen, we have 1 electron. And from oxygen, we have 6 electrons. So that's a total of 8 valence electrons available. Okay. Next, what you want to do is take the atom that you have the fewest of and put it in the center. So I'm going to put an oxygen here in the middle, and on either side, I'm going to put a hydrogen. Then I'm going to draw a bond to each of those, and then I'm going to satisfy either my octet or my duet rule, meaning that hydrogen will have 2 electrons around it, which if you look, hydrogen has 2 electrons with it. It's sharing that pair. So does the other one. But for oxygen, I'm going to have to give it 8 total electrons around it. So if I look just around the oxygen now, I've got 8 total electrons around it. So I have obeyed. I've found the number of valence electrons I have. I have obeyed the octet rule by writing everything there correctly, at least 8 around everything that would have 8, hydrogen with 2. Now I go count and see if I actually have the right number of valence electrons drawn. Each of these counts, let's eraser, counts as a pair, counts as a pair, counts as a pair, counts as a pair. So I have actually 4 pairs of electrons, or 8 valence electrons. This is the correct structure. Now you'll see water drawn a couple of different ways. We're drawing it in 2 dimensions. As we get further in the unit and we talk about valence shell electron repulsion theory, don't worry about that today, but we will need you to kind of understand that it has sort of a different shape. So if you see it drawn the way it is on the bottom here, rather than the way it is, in the middle of the screen, it's fine. It means the same thing. You're just looking at the water molecule in a different plane. So we have a 2-dimensional plane on the screen, right? So, but water has a bent molecule. It looks like this with hydrogen down here, and oxygen in the middle. But if you looked at it straight up like this, it would kind of look like it were in a line. It would look like this if you were looking at it from a certain direction, and it would look like it does on the bottom if you look at it in a different direction. So a couple of different ways to see water drawn. And so it's drawn here kind of the same way, linearly, but it actually is a bent molecule, but that's okay. So remember that all we're trying to do right now is get the right number of electrons around them and kind of set them up. Let's do another one. So the first one on the left is going to be ammonia. And on the right, of course, is the polyatomic ion ammonium. But ammonia, let's count the number of electrons. Nitrogen is in column 5, so it would have 5. Hydrogen, each of the hydrogens, column 1, so it would be 3 total electrons from the hydrogen. That would give me a total of 8 electrons. The one that I have the fewest of is nitrogen. Big hint, hydrogen will never be in the middle of an atom. It can only form a single bond, so it has 2 electrons. So it'll never have things all the way around it. So something other than hydrogen will have to be in the middle. So nitrogen, I'm going to draw hydrogens around it. And I have satisfied the duet rule for hydrogens. If I put 2 more electrons on nitrogen, I have now satisfied the octet rule for nitrogen. And if I count, I have 8 electrons. That is the correct structure. Now let's look at ammonium. Ammonium has a nitrogen, a hydrogen, a hydrogen, a hydrogen, and a hydrogen. And I did this out of order, didn't I? I drew it first, and now I'm counting my electrons. It's not the end of the world, but make sure you don't skip that step. So nitrogen has 5, each hydrogen had 4. I need to take 1 off because this is a positive charge, and that'll give me a total number of 8 electrons. If I look at my structure, it has 8 electrons. It is correct, but it is an ion. I took an electron away. If I added electrons, I'd have to do the same thing. I'm going to put brackets around it, just like we did for the dot structures for single atoms, and write the positive out there. Now on the atoms, we didn't do it for positives, but for multiple atom molecules, or for molecules that are made up of many atoms, you must put brackets and charge on all of them. Okay. And so if I scroll up, there we go. There's what it looks like. 9 minus 1 is 8. Good job, Talon. Okay. So let's look at this. We got CO2 on one side and CO2 on the other side. One of them is going to be bad. Well, I'll show you. So carbon has 4 electrons. Each oxygen has 6. So 4 plus 6 plus 6 is going to be 16 electrons. So I'm going to go do this over there on the left side and use the right for something else. But anyway, okay. So 16, I'm going to put a carbon in the middle. It's the one that I have the fewest of. I'm going to put oxygens on the outside. And now I'm going to give everything 8. That's all I do is make sure I give them all 8. And then I'm going to count how many electrons I have. So what I have is 8 and 8 is 16, 18. I have 20 electrons. That cannot be right. I'm only supposed to have 16. So one way to do this, and Miss Aiken has a cute little saying, she says, I forget, it's take a pair and create and share, or I don't know, take 2 pairs and then share. I don't know, but I don't have her wit. But what you do is you're basically going to take, I'm going to draw the exact same thing over here just to kind of show you, but this is not correct. So what I'm going to do is draw it over here and then kind of show you what to do. And then we'll be able to compare the two and show you the difference. So over here, I've got 20, but I only need 16. What you do is take your eraser and take 2 off from one of them and 2 off from the other one, and then create a double bond between them. By doing that, everything still has 8 around it, but in essence, I have deleted 2 total electrons from there. So now I'm down to 18. Can you think of a way to delete 2 more electrons so we can get down to 16? I bet you can. Take these 2 away and these 2 away. So take away 2 pair and then share. I think that's what she says. I can't remember. But you're going to share a pair of electrons between them. And so now if I go and I count, I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. That is the right structure. So if you get to a point where you've got too many electrons, you take 2 pair away from each, and then you share a pair between them. So if I scroll down here and show you, oh, I know, the smiley frowny faces. The one on the right is correct like we drew. And so creating double bonds, this isn't how it's done molecularly. This is just a cute way to kind of figure out how to do it. Don't think that atoms are adding electrons and then subtracting them. That's not real. That's just a way of us doing this. Okay, so let's go do another one. Actually, you guys do this one. Put me on pause, go count your electrons, draw your structure, and come right back. Okay, so if you're back, let's say 4 plus 28 is going to be 32. I'll put a carbon in the center, chlorines around the outside. And then if I go and give everything 8, I'm doing really small dots. I apologize, not making them big and fluffy like before, but oh well. There we go. So now what I have is, if I count 4 times 8 is 32 electrons. This is the correct structure. Ooh, yay, go Tollett. There it is. Ooh, I got another one. And look, we got one side and one side, so probably something's going to go wrong here. Let's count how many electrons. 4 from carbon, 5 from nitrogen, and a negative charge means we have to add an additional electron. So we have 10 total electrons. So I'm going to put a carbon on one side, a nitrogen on the other side, and I'm going to draw all my dots, and then I'm going to count. And if I count, I've got 2, 4, 6, 8, 10, 12, 14 electrons. That's not right. I can't have 14 electrons. So this is not correct. So I'm going to draw it the same way over here. Ooh, making fluffier dots. Let me go. Okay. And remember, if you have too many electrons, you take a pair from each and then you share a pair. So I'm going to take away these 2 pairs on top, and then I'm going to go back and share a pair of electrons and then recount 12. That's wrong. I can't have 12. So I just do the same thing. I'm going to subtract these 2 here on the bottom, 2 pair that is, take those 4 electrons away, and then put my double bond, or triple bond, sorry. If I count, I've got 2, 4, 6, 8, 10 electrons. This is the correct structure, but I almost forgot. I need to put brackets and charge on ions for Lewis dot, or Lewis dot structures require that I put that bracket and charge so that I know that there's an extra electron there. Good. See, this isn't so bad. Okay. Oh yeah, look, smiley frowny. Too many electrons on the one on the left. Sulfate. Okay. There are a few different ways to draw sulfate, and there's a method called formal charge to solve for the correct way to draw it. You guys don't need to worry about that this year. We'll attack that next year if you happen to run across it when you're looking at things on the internet. We just really want you guys to be able to draw them correctly, whether or not you obey formal charge or not. So the numbers of electrons, sulfur is in column 6, as is oxygen. I'll add the 4 electrons, or the 4 atoms of the valence electrons for oxygen. It would be 24. And then I'm going to have 2 additional electrons from my charge. So 24 and 6 is 30, is 32. I'm going to go and put a sulfur in the center. Oxygen's around the outside. And then I'm going to give everything 8 on the quick, not so fluffy dots. Yeah. If I count, I will have 4 times 8. There's 8 on every outside part, is 32. It's finished. What do I need to make sure I add? Brackets and charge. And that is the correct structure. It's kind of neat. I mean, this is very different than what we've done in chemistry. We're not done. There's going to be more interesting, different things. But yeah, this is certainly different than what we've done before. And like I said, you may look up sulfate online and see that it has a different structure than this. It's very similar, very, very similar, but it looks a little different. And maybe when we get back a little later, I'll show you how to figure that out. I haven't decided whether I'm going to teach you that yet or not. But this is fine. Totally acceptable for you guys. So carbonate. All right, so carbonate, why don't you try carbonate without me? Yeah, go try to do this. Hit me, pause me, quit listening to me, and go try this for a second. And then come back and I'll show you how I did it. Okay, so assuming that you did that, I've got 4 plus, let's see, 3 times that'd be 18. 2 additional from the electron would be 24, or from the charge. So I'm going to have a carbon in the center, an oxygen around the outside, and it would look like this guy here. Now you can't stop there. That's 24 electrons, but don't do that. Make sure you give everything 8, like the rule said, then go back and check and see how many you have. Well, this has 26. It's too many electrons. So if I redraw it over here and kind of show you the right way to do it. I would need to create a double bond with one of the oxygens. Oh, which oxygen? It doesn't make any difference which one you choose. Just to be difficult and be a jerk, I'm going to take it from here and take it from the bottom, and I'm going to drop the double bond to the bottom just to make you nuts. But it could have been any of the three. And that's something I'm going to talk about in a little bit called resonance, where actually the bond could be in any one of these positions. In reality, it's not in any of these positions, but for our drawing purposes, it is. And in this particular case, I would, of course, need to write my brackets and my charge before I could actually get the correct structure. But if you drew it with the double bond to one side or the other, not down, it's still correct. You would still get totally full credit. But we will describe that phenomenon a little bit later. Ooh, look, smiley frowny. Okay, there we go. Yeah, this one down here on the bottom, they didn't even finish drawing all their electrons. You know, it doesn't meet the octet rule, though, with carbon only having 6 around it. So don't do this. Make sure you check and make sure each one of the atoms actually has 8 electrons around it. All right, cool. So a coordinate covalent bond, I mentioned this earlier, but I didn't tell you what it was called. When you have a species that donates a pair of electrons for that individual bond, as it does in ammonia, it's just called a coordinate covalent bond. The bond is the same. It's not treated any differently. It just means that the 2 electrons of nitrogen are what's being donated here for this bond with this hydrogen. It's just an aside, just something that vocab kind of thing you need to know. But coordinate covalent bonds mean that the 2 electrons come from the same species. They're not sharing one each. They're sharing a pair offered by one individual atom. Okay, so we're going to stop there. We'll do some more practice in the next lesson, and we'll also talk a little bit about where that double bond's going to be in those other ones. Okay, so I'll see you in the next video.